Liking.
Welcome everybody to the February FPGA seminar. Today we have some recent alumni talking about their entrepreneurial experiences trying to commercialize LegUp. So Andrew Hannes and James Choi speaking.
Okay. Thanks so much, Paul. So as Paul mentioned, we're former PhDs and grad students from the CC department, and we've spun out our compiler research into a startup, which is now funded by Intel. So we're just going to give a brief overview of the company and some of the stuff today. We have some recent alumni. The kind of core premise behind the company is this idea of high-level synthesis and taking C and C++ software and then turning that into something that runs on OS. So as I mentioned, the company started with myself. I was doing my PhD also with James. Going to talk to him a little bit. Lenny was doing his master's, and this research was supervised by Jason Anderson and Stephen Brown. And they've all, both Jason and Steve, been really helpful in just commercializing this effort with us. And also, when we got some Intel funding earlier last year, we managed to hire kind of a couple other people. G and Omar, who are also here, also graduates from the EC department. And also Mehul, he's a co-op from Waterloo, who we just had this term. So that's the team right now. So just a little bit of background on the company. So the technology was developed over about a decade now. So it started in 2009 with my PhD. And essentially, that LegUp compiler tool, we first released it open source. And those initial papers have got a lot of citations as academics just download the LegUp compiler and then play around with the various different algorithms. And when I graduated from my PhD in 2015, we decided to try to commercialize it and see if we could basically sell this compiler to actual real engineers who want to program FPGAs. And our office is just located a couple blocks away, across from the Mars building. And as I mentioned, we got some seed money from Intel earlier last year, which we really appreciate. So kind of stepping back a little bit, kind of the broader industry trend, what we're seeing is basically Moore's Law is just slowing down a little bit. And what you're seeing is NVIDIA, Google, they're developing these custom ASICs that we all know about, like GPUs, TPUs that are targeting machine learning. And the idea is, why couldn't we also target an FPGA? And then we have access to reconfigurable hardware, and FPGAs are really good at kind of real-time processing of a lot of data at high throughput and also with low latency. And this might be a little bit of review for some of you, but I'll just go into a little bit of why is an FPGA, how is an FPGA different than a CPU? So if you look at a normal CPU, essentially what's happening is it's fetching a bunch of instructions and then executing those instructions at a very high clock speed and has kind of very simplistic kind of operations. Whereas on an FPGA, typically what you're doing is you're fixing all those instructions into hardware with a very, very deep pipeline, and now you're feeding the data through that basic piece of hardware. So that's kind of fundamentally where a lot of the speed up's coming from. And I'll just give another little example just to drive it home. Let's say we're doing some packet processing on the CPU. Basically, we receive a packet, we do some processing, and then we send it back out. If we're looking at a CPU, as we process each packet, they're going to be processed sequentially. So each packet is going to take some kind of quantum of time. Whereas on an FPGA, what you can do, because you can have such a deep pipeline on the FPGA, you can actually feed in more packets and kind of process those packets in parallel. So you have a super deep pipeline, and the packets are being processed completely in parallel. And the benefit of this is you get higher throughput, meaning you can start a new packet more frequently than you could on the CPU, despite the fact that the clock frequency of this might be a lot higher than the FPGA. So you have this extremely deep pipeline. So the interesting thing about this is, let's say we want to increase the processing that we perform on each packet. So basically on the CPU, this quantum of time will get longer and our throughput will decrease. But on an FPGA, because we can just make our pipeline and our data path deeper, we actually don't get a throughput hit. So I think this is probably intuitive to everyone in this room, but probably to a lot of software guys, this you probably have to drive this home a little bit and explain to them how this is possible. And this I see as one of the main benefits of an FPGA. And when we're thinking about where can an FPGA beat a CPU, I see it as kind of breaking down into two main categories. There's this thing I was just talking about, this high throughput line rate processing that you can perform. And the reason you can do that is, as I mentioned, you have these deep data paths on the FPGA. You can widen your data path pretty easily if you want to process more network bandwidth. So, for instance, a recent example we saw is Twitch, which is a kind of video gamer platform where you can live stream yourself as you're playing a game. They actually are rolling out a data center with a bunch of FPGAs powered by NG-codec. Basically, NG-codec has a video decoder that can reduce the bandwidth usage. And the reason why you would use an FPGA is because this is all live video as you're watching the games. You can't really batch it off to kind of a cluster of CPUs. You want to be encoding that video in kind of live without much of a hit to latency or anything like that. So basically, they can save a lot of bandwidth by using FPGAs. And also, you see kind of FPGAs being used in network switches, and also we saw, a couple months ago, Microsoft came and they're using it for Bing Search too. And kind of breaking it down into a table, let's assume you have a 10 gigabit per second network link that you're trying to process at real time. And let's say we have one core operating at 3 gigahertz. We only actually have a couple clock cycles for every byte. And as we go up from 10 gigabits per second to 25, 40, you have less and less time on the CPU. So you just start getting bogged down if you want to process this at line rate. Even if we go up to 32 cores, it's not much better. But on an FPGA, you can just make that data path so much deeper. You can have thousands of cycles to process that data. So you can just keep up with line rates, and you can also widen the data width too. The other big usage that we found of FPGAs are kind of on the low latency side. And really, this is just because the FPGA, as I mentioned, it's not executing instructions. Everything's kind of hard-coded. So the latency can be much, much better than running on a CPU. And you see this with some of these smart NIC applications people are doing to speed up software-defined networking. The classic one is also high-frequency trading. These guys can receive a packet from the network, the market feed, and then respond in tens of nanoseconds, which is pretty incredible when you think about it. And also, kind of on industrial level, there's also things like motor controllers where you really do care about very fine-grained latency and control over those motors to get the best performance and safety. Yeah, so that was kind of the brief overview. And then basically, when we look at FPGAs, we all know this, that they're pretty difficult to use. You need specialized skills. So when you're targeting an FPGA, you have to do RTL design, look at simulation waveforms. Whereas in software, you're just working with C, C++, you have debugger infrastructure, all of this. And FPGA, typically a design might take months, which from a software perspective is a really long time. Normally they can spin up pretty complicated design in a couple of weeks or something. So really kind of the problem here is FPGAs are pretty difficult to program even for hardware designers. So even for hardware designers, it might be nice if you could program from C++ or C. For software engineers, it's really difficult for them to use FPGAs, just period. So kind of the main product of the company is this LegUp compiler that we basically license and try to sell. And basically what this is a platform that allows you to take C++ code and then target any FPGA. So we could target Intel FPGAs, Xilinx FPGAs, and the customers like this because they're not kind of stuck to one particular vendor. They can switch between. They're not stuck to Xilinx, for instance, with Auto HLS. They can switch over to Intel. And also some of these smaller FPGA vendors like Acronics, Lattice, Microsemi, you might have heard about them less, but they don't even have any high-level synthesis technology. So for them, kind of this platform is also very useful. They don't have any other options. So that's kind of the core product. And you might be thinking, how do you program the FPGA starting from a language like C++? And typically what we're doing is we're taking advantage of kind of a data flow model where it really matches well to the pipeline parallelism I've been describing of an FPGA. So essentially, I just have a little simple example here. We have 4 different kernels. The idea is each one of these C++ functions is going to be executing concurrently. And each one of them is going to be pipelined, so they're receiving a new piece of data every single clock cycle. And what we do is we connect them using this FIFO data type, which semantically is similar to a queue in software. You can also call it a channel. Some people call it, there's different names for it. But basically, essentially what it's allowing you to do is kind of read a piece of data from the FIFO and then write it to another FIFO. So that allows us to run all of this in parallel and really take advantage of kind of a very deep data path, which is kind of the main benefit of an FPGA. Also, a FIFO has an efficient implementation on the FPGA. So we released the LegUp tool commercially when we first launched, and we've done a number of different releases since then. We try to keep up with a 1-month cadence, so we did the last release beginning of February. And you can just go to the website, download it, get a 30-day free trial. Has support for both Windows and Linux. And some of the key features that we offer that some of the other high-level synthesis tools don't have are things like support for P threads and OpenMP, so allow you to express parallelism in your C++ code. So similar, if I just jump back to this one, you ideally want each of these kernels to be running in parallel. So it kind of maps pretty well with kind of multi-threading kind of concepts from software. And also we have work for my Ph.D. around really good loop pipelining and function pipelining. And also we support push-button system-on-chip generation. You can connect to like an ARM processor, for instance, on an Intel device. And vendor agnostic is another key differentiator. So basically how this looks is similar to maybe Vado HLS if you used it before. It's basically an Eclipse IDE where you program your software application in the main kind of window, and then you can click a button to compile that software into Verilog. And then automatically you can click synthesize and we'll call the appropriate backend vendor tools. So if you're targeting Xilinx, we'll call Vado. If you're targeting Intel, we'll call Fortis. And you can also run all your simulations out of this environment. So it's kind of a one-shop place where you can just do your design. And I'll talk about some of the kind of recent things we've been working on, some of the ideas we've had as we've seen kind of customers kind of using this tool. One of the things we've noticed is kind of traditionally high-level synthesis, it's treated as kind of IP core generator. So basically you define a function, and that term maps into kind of an IP block. And then you'll take that IP block, keep repeating this for all the blocks in your design, and then you'll rely on kind of our favorite QSys or IP integrator for Xilinx to connect those blocks together into a larger system. But the problem with doing this, I mean, some people even use RTL to connect these blocks just by hand. But the problem is it's pretty tedious. You have to use that graphical interface. You know, it's hard to iterate when you're doing it like this, just generating these individual blocks. So one of the ideas we had recently was basically this idea of system-level synthesis. So what if, you know, right now it works, you know, you generate one block, turn that into hardware. But what if you could describe the entire system, including connections between those blocks, all in software, and then generate an entire system? So these connections between the individual modules could be, you know, AXI-stream inferred from those FIFOs that you have in software. And basically now you describe the entire system. Well, what if one block doesn't have the performance that you wanted? Maybe the HLS tool just kind of messed that one up. We also have this custom RTL facility where you can actually specify one module in Verilog or VHDL. So you basically specify that one particular module in RTL and still connect it together using the system level kind of generation. So that could be pretty helpful, particularly for, let's say, an IP core. Like, let's say if this is like a DDR controller, you don't really want to be writing that in HLS. You kind of want to just have the vendor-provided RTL block, basically, and then just connect it to the pins on the FPGA. So LegUp is kind of a system-level HLS tool. The idea here is, you know, a user could describe the entire system in C++, making those connections with these standard kind of APIs that we described, like these FIFOs, and we support various different protocols. And this provides flexibility, as I mentioned, for custom RTL blocks, which is, you know, this target market for this kind of flow wouldn't be a software engineer. This would be more like a hardware engineer who understands FPGA pretty well. But basically, if you understand hardware, it is really nice to have this level of control. And let's say I have a vendor-provided IP core, I can just use that. And then in software, I can replace it with kind of a software-based version that's maybe reading from a file so that I can simulate this whole system and do, you know, hardware-software co-simulation to verify the entire complete system. And in future, what we want to do is integrate with things like chip scope and basically signal tap, and basically allow you to annotate kind of the borders of those modules, which are typically AXI-stream, kind of FIFO interfaces, and allow, when it's running on the board, you could actually see the data flowing through those modules to allow you to do better kind of on-board debugging. We think this is kind of a cool thing that we've been working on recently. Another thing I want to talk about briefly is kind of how does the performance of the HLS tool compare to, you know, handwritten RTL. So one recent thing we've been working on is kind of a floating point library entirely described in C++. So you could think of this as kind of your traditional IP core library of floating point units. They'd all be written in Verilog or VHDL. They'd all be written in RTL. But what if, you know, you describe those blocks in C++? What does that give you any benefit? And basically, the nice thing about using C++ is you can use all sorts of template parameters to really configure that floating point unit. So for instance, let's say if you're targeting different FPGA architectures, one FPGA architecture has different DSP widths, for instance. Like Microsemi has different FPGA widths than Xilinx, for instance. You can actually encode all of that inside your C++ templates, which would actually be pretty annoying probably to try to do all that in RTL. Also, let's say if you have different target clock periods, in RTL, how are you going to really express that? You have to have all sorts of if-defs and parameters in your RTL. It gets a little bit tedious to do. So the idea is, with this library, you can specify exact levels of different precision. So you could specify your mantissa width if you want half precision, 64-bit double precision, and the FPGA can be tailored exactly to the precision you want. Some people doing machine learning might not want the standard IEEE compliant floating point. You could just modify it here yourself in the C++. It's not too bad. And this is vendor agnostic, so it's targeting any FPGA. And we posted one of these last month to our GitHub, and we're still working on kind of the remainder of them before we release them. But interesting thing we noticed when we were targeting kind of a Microsemi device is so when Microsemi provides some floating point cores, for instance, a 32-bit single precision multiply. This is all just written in RTL, and you can generate this core. By default, it has 8-cycle latency. The Fmax was around 200 megahertz. And then also we had a third-party provider who had RTL blocks, again, for the same thing, a 32-bit single precision multiply. And that one was kind of similar, had a bit better Fmax. The resources were somewhat similar, a little bit different. But we thought, how would we compare to this if we re-implemented in C++? And we were kind of surprised to find, actually, the LegUp implemented version was actually better performance than the handwritten RTL. So we had, better Fmax. The LUTs were a little higher than the Microsemi provided one, but pretty much on par with the third party. And the registers were lower than both of them. So it's kind of interesting that you can take C++ and actually generate something that's better than hand RTL. We were a little bit surprised by this. And then also, one of the advantages is we actually needed to go up in clock frequency for our particular purposes for this design. And, you can swing around, the first, before we even implemented this, we tried adding input and output registers. The Microsemi one kind of got us up to 300. But on the LegUp one, you can kind of swing around that latency very easily to achieve, better Fmax, play around with the register usage. And, it's just much more flexible when it's described in C++. In terms of targeting a different FPGA vendor. Like this third-party IP was probably written for Xilinx, so probably they hadn't tuned the DSPs, appropriately for Microsemi devices. All this kind of stuff is just much easier to describe in C++. And I think Jason Anderson also has some papers on this. Just kind of a really cool thing that we've been noticing. So kind of moving forward to, and I'll pass over to James soon, but kind of another exciting thing happening in the industry is this idea of FPGAs being used in the cloud. And the trailblazer here was Microsoft with their Bing Search and all their kind of brainwave project. But Amazon Web Services now allows you to spin up an FPGA in the cloud. Same with Alibaba, Tencent, Huawei. And the idea is we were thinking, how could we make it easier for a software developer, to use these FPGAs in the cloud? And one way we were thinking is they could define their application in C++ and use LegUp to target kind of a pre-built shell, essentially, where we provide essentially the network stack, the TCP, UDP layers, which we've also developed using LegUp HLS, but we can kind of hide that from them so that if you're a user kind of implementing a standard piece of computation, you don't have to worry about the very low-level details of the network stack. So that's kind of one thing we've been working on, and I'll just pass over to James to talk about kind of an application we did kind of using this model.
Thanks, Andrew. So we were very excited about these FPGAs being available in the cloud, so we wanted to try it out. So the first application we implemented was this application called Memcached. I presented this at last year's Hard Conference, so for those of you who were there, this may be review. But Memcached essentially is, you can think of as a caching database. It's used very frequently by these very big internet companies such as Facebook, Twitter, and so on that have kind of millions of active users at a time. And how it works is that the Memcached is deployed between kind of the front-end web server and the back-end database. And the front-end web server will make requests to Memcached and quickly get data from the cache if it's available. Otherwise, it will access the database to access the disk. Like I mentioned, it's used by these companies, Facebook, Twitter, Reddit, and YouTube. And Facebook actually published a bunch of papers on Memcached where they have these huge clusters of CPU Memcached where they can handle billions of requests per second. The major Memcached commands are essentially get and set. So it's a cache, so you can think of it as store and a load. And how it's typically deployed in a commercial environment is many companies use AWS. So on AWS, they have a service called Elasticache. It's a managed service, meaning that they install everything for you, everything's already set up. Essentially, all you have to do is you go to their website and you click a few buttons and you spin it up right away within a matter of seconds. It's very easy to use. You tried using it multiple times also. And you just have to point your web server to the IP that is given by AWS. So it's kind of a service fully packaged provided by AWS, and many companies use this. And Google obviously has a computing service. But some of these other big companies who have their own data centers also host it themselves in turn. So what we did was we took this Memcached application and we implemented on the F1, AWS F1, that's the AWS FPGA cloud. And this is how the FPGA F1 instance looks for those of you who are not familiar. There's an FPGA, this is Xilinx UltraScale Plus FPGA, and there's a CPU also. And the FPGA isn't really directly connected to the network. FPGA is connected to the CPU over PCIe, and the CPU itself is connected to the network. So on the FPGA, we implemented the entire Memcached application here using HLS. And because Memcached receives data through network packets, we also implemented the TCP/IP stack on the FPGA using HLS as well. And since the FPGA is not directly connected to the network, we also have to implement this bypass architecture where when the packet arrives to the CPU doesn't decode it. It sends raw packets directly to the FPGA for the TCP/IP stack on the FPGA to decode. So that allows much higher throughput processing of network packets at a lower latency compared to doing on a CPU where the OS would be involved. As mentioned, FPGA also has a 64 gigabyte DDR4 RAM, which is used by the Memcached to store data. So kind of to just jump to the conclusion first, we implemented this on AWS FPGA, and we think this is the fastest cloud-hosted Memcached. And when we compare this to the Elasticache service that I mentioned that's offered by AWS, we were able to see 9x higher throughput. So throughput is measured in terms of requests per second, so number of nodes, number of stores that you can handle per second. 9x lower latency, and that leads to 10x better total cost of ownership. So let me just show you how we got these results. So this is how we set up the experiment. So this is the FPGA instance that has the Memcached accelerator and the TCP/IP stack. This is the Elasticache instance that's offered by AWS, running a CPU. And also on AWS, we're running another CPU instance that acts as the client. So this client is going to run this M-tier benchmark. It's a standard open source Memcached benchmark that's frequently used to measure the performance, latency of Memcached instances. And this client will send a bunch of requests to Elasticache, measure the throughput and latency, and then subsequently, using the exact same client, we'll send a bunch of requests to the FPGA instance to measure the throughput. If you actually go to our website, we have a live demo. You can try it yourself. If you just go to this link, it's very easy to use. You just have to enter a couple information. We will actually spin up the FPGA instance for you, program the FPGA with our accelerator. We'll also spin up the CPU instance running Memcached benchmark, and you can measure live the throughput and latency of our Memcached accelerator. And of course, we will pay for the AWS instance as well, so everything is free. For today, typically we used to show an actual live demo, but we've shown this so many times now, so we actually recorded a video. So let me just show you a recorded version. So what we're showing here is 3 windows. So top right, this is the AWS console window. This is where you kind of spin up these instances for the FPGA, Elasticache, CPU, and so on. The bottom, so top left is the terminal that is running on the FPGA instance. And the bottom is the terminal that's running on the CPU instance that's going to run as the client. Okay. So on the top right, we're showing the Elasticache instance that has been spun up. And if you continue playing this, we are showing kind of the FPGA instance and the CPU instance for the client. And what we're going to do is we're going to copy this configuration endpoint, which is essentially the IP address of Memcached. It's showing the type of Memcached, and going back to the client. We will now run this benchmark. Let me just plug it right here. So this is the benchmark that's gonna send a bunch of requests to the Memcached server. What we're doing here is we're going to send data packets that are 100 bytes each. There will be 32 threads running. Each thread will make 10,000 requests each. And on the server line, we're essentially going to copy the IP address of Memcached. So you can see that it's running. It's sending a bunch of requests now, and it's measuring the throughput latency as it's making the request. And once it's done, it'll show kind of a table which shows the average throughput and latency. So what we're showing here is that it's on average, the throughput is 1.27 million requests per second. That's what it's able to handle. In terms of latency, each request is taking about 13 milliseconds. So now what we're going to do is we're going to spin up the FPGA server. So we're going to program the FPGA and start running the application on the FPGA. And we're going back to the console window to get the IP address of the FPGA server. And we're going back to the same window. All we're going to do is we're just going to change the IP address of the server, and it'll run, and then boom, it's done. So because it's able to handle much higher throughput, the benchmark finishes really fast. So it's saying that it's able to handle about 11 million ops per second. Each request is about 1.46 milliseconds. So that's about 9x fast, higher throughput, 9x low latency. We're actually going to increase the number of requests because that was really short. Just to kind of get a better average, we're going to basically 10 times the number of requests for each thread, so it'll run for a longer time. And again, it's showing a similar result, 10.8 million requests per second at about 1.5 milliseconds of latency. So kind of looking at the three different results, the CPU, Elastic Cache Instance, showed 1.27 million requests per second. The FPGA results are showing about 11 million requests per second. So we were able to get much higher throughput and much lower latency using the FPGA on over this class. So that was kind of an overview of the technology side of the company. We also wanted to talk a little bit about kind of how we got here and kind of the things that we learned as we commercialize this technology. I think most people will be interested in that. So as Andrew mentioned, LegUp started in 2009 as a research project, and of course the motivation was to make FPGAs easier to program. And we decided to open source a framework, as Andrew mentioned, to have lots of researchers around the world to be able to use the framework, to contribute to it, and use it for their own research. And we were having regular releases. Over the course of the project, lots of different people contributed. It isn't just us that are here. Actually, more than 30 graduate and undergraduate students contributed to the project, which was very helpful. We published lots of papers, over 25 papers during the time that we were here. And we are having lots of collaborations with different universities, including UBC, University of Waterloo, and Imperial College and so on. And back in 2015, we transferred the IP at that time out of the university into the company to start to commercialize it. So this kind of shows overview of what we've done so far. So in 2009, it started as kind of 3 master students, Andrew, myself, and Mark Alden. And we've had kind of regular releases, 2011 March, 2011 December, 2013, 2015. So we had 4 academic releases from 2011 to 2015. And during these releases, there were about 5,000 downloads of the academic tool from different researchers around the world. And then we incorporated a company. We were lucky enough to kind of have a first customer right away when we incorporated, which really helped us get us going and survive as a company. And we took kind of all this technology that we developed at the university. We flushed out all the bugs. As you know, academic projects have lots of bugs in them. So we spent a bunch of time flushing out all the bugs, and we're still doing that. And we made our first commercial release in 2017 in July. We made kind of a nice front-end GUI that Andrew was showing. We added support for different vendors, Addison like Microsemi, and also Windows support as well. Since actually lots of customers prefer Windows over Linux. Very different than Raspberry. And then we raised seed capital last year, and with the seed capital that we raised, we were able to hire these very smart guys, Omar and G, who helped us implement this Memcached accelerator on AWS. And Xilinx actually really like this because on AWS it's Xilinx FPGAs, so it's a really good showcase for them to say, FPGAs are really working well on the cloud. It's able to get this, massive speed up over a commercial CPU service that's used by a lot of customers. So we joined the Xilinx Partner Program in last year, and Lanny and Andrew actually went to Frankfurt to showcase this this work at the Xilinx Development Forum. And very recently, again, we had our latest release, LegUp 6.6. So we also wanted to share kind of some of the things that we learned. We learned a lot kind of during the last 3.5 years while we were in startup. We are still continuously learning. But I wanted to share kind of some of the, I guess, most important lessons that I've personally learned. The first is, I think the team is actually the most important asset for a company. More important so than the technology or the product itself. You really need a good team to develop and make the company a successful company. There will be lots of hard times, trust me. So you have to be able to trust each other and rely on each other and kind of work together and push forward even through the hard times. And really, if you have a good team of 4 people, you can really build anything. So I would say the team is the most important factor for a startup, for an early stage startup. For investors also, kind of that's the thing that they look at. For an early stage startup, you don't really have any customers, you don't really have a fully furnished product. So the team is actually what they think is the most important as well. This point seems pretty obvious. Build what your customers want, not what you want. Actually, it's a little bit harder in practice. I think engineers typically think, they know what the right thing is to do, but it's oftentimes it's very different than what customers want. Engineers, have this mind where everything has to be perfect, the code has to be, very clean. They tend to want to build this very complicated stuff, but lots of customers actually don't want that. They want like very simple stuff that just works. So you really have to think about what your customers want and talk to them, get feedback from them, iterate on that rather than just kind of thinking by yourself and kind of coming up with something, spending a bunch of time rolling it out. Roll it out as fast as you can and get feedback from them. And kind of towards the same line, really speed of execution is key for an early stage startup because you really don't know what's going to work, what your customers are going to pay for. So roll it out as fast as you can, get feedback from customers, and then move on from there. So the speed of execution, this iteration, I think, is very important for a startup. So why would you actually want to work at a startup? Definitely there is more career growth. You get a diverse set of experience working in a startup compared to a big company. Because you're not just assigned to one role, you kind of have to do everything. One day you're coding C++, next day you're doing RTL, next day you're going out to customer visits, next day you're going out to expos, next day you're having meetings with company execs. So really you're wearing multiple hats, doing everything at the same time. So for an early kind of grad, I think this would be a very useful experience for as a career growth, and you can kind of get this diverse set of experience, even if you're going to work at a big company. This will be very important for you. And really it helps you see the bigger picture because you're not just an engineer, you're not just coding every day, you're not assigned to this one task that you just have to implement and make it really perfect. You have to think about, where is the market going, what is the customer going to pay for, and so on. And the last point here really is, I guess, also applicable for early stage startups is you can really make a big impact on the company because everything you do will be shipped to the customers and everything you do will kind of drive the direction of the company. For instance, Nehal, our co-op who actually just joined us last month, everything that he's doing is going to be shipped to customers. We had a U of T intern last year who implemented a compiler pass. Everything that he implemented is being shipped to customers. So you can really see the direct impact of your work and how that changes the company, which is actually very good for us. So with that in mind, we are hiring. So actually, that's the main reason we're here. We want to hire very smart guys like you, who can kind of help us go further and take the company and make it a success. So what is it like working with us? We are very fast paced. Like I mentioned, speed of execution is key. We try to roll out things as fast as we can, and we iterate on that. It's a very collaborative environment, though. All of us, have a very good relationship, and we work very closely with each other. We literally sit like a couple feet away from each other, so it's a very collaborative environment. And like I mentioned, everybody works on everything. This will really help you learn a lot, get a diverse set of experience. You're working on compiler, you're working on RTL, you're going to conferences. So Randy's actually going to a FPGA conference next week, and then he has a couple of customer visits afterwards in the Bay Area. And you constantly have to look for new applications that will work for FPGAs and also for HLS. Because in reality right now is there isn't really that many applications that have been a huge success for FPGAs in the acceleration domain. So you're constantly going out and finding applications that work that we can ship to our customers. And we constantly have to meet with our customers and talk to different people from different countries. So of course you'll be working with domain experts. All of us here in our team are HLS and FPGA experts. And everyone really works hard to make the company a success. And we will of course train you to get up to speed as fast as we can. And like I mentioned, what you're doing will be making a big impact on the company. So what we're hiring for right now, kind of these titles really don't matter because you'll be working on everything. But this is kind of the work that we're doing. On the compiler side, of course, it's a lot of implementing C++ stuff on the Elegant compiler, which is what our compiler is based on. And on the FPGA side, you'll be building kind of IP libraries that are built in RTL and also in HLS for application domains. And some of the application domains that we have been looking at are networking, as Andrew mentioned, and machine learning and computing. So if you're interested, please do come talk to us afterwards today. And also you can send us an email at jobs@legcomputing.com. Thank you very much. Happy to take your questions.